Next keynote speech is by Dr. Takaaki Matsumoto, titled The Role of Software for Realizing Dependable Cyber Society. Let me introduce him. Dr. Takaaki Matsumoto is President SEC in IPA. He received a doctorate degree in computer engineering. After working for NTT, he is currently President of Software Reliability Enhancement Center, SEC, at Information Technology Promotion Agency, IPA. Please join me in welcoming Dr. Takaaki Matsumoto.
Thank you, Mr. Chairman. Good morning. I'm Takaaki Matsumoto of IPA. It is my great honor to be here in APCOSEC2013. Today, I'd like to talk about the role of software in realizing cyber dependable cyber society. Before going into the main topic, let me briefly explain about organization. IPA is an independent administrative agency sponsored by the Ministry of Economy, Trade and Industry of Japan. Independent administrative agencies engage in business that should be conducted from the public viewpoint. But need not to be carried out by the government directly or by the private sector because of profitability or competition. Currently, there are 102 independent administrative agencies in Japan. IPA was established in 1970, but was reformed as independent administrative agency just 10 years ago. Our goal is the realization of an IT-based society where people can live their lives feeling secure. And Software Reliability Enhancement Center, or SEC, to which I belong, is the technology headquarters of IPA. And technology headquarters have also 3 centers, including the IT Security Center and the Open Standards Promotion Center, in addition to SEC. I suppose that you can tell the roles of these centers from their name. And the IT Security Center is also committed to the mobile security, which has been drawing attention recently. This topic will be discussed in the IPA SEC special session, which will be held this afternoon. So those who are interested in this topic are encouraged to join the session. SEC is committed to the improvement of reliability of IT systems that support society. SEC was established in IPA as Software Engineering Center in 2004, focusing on development and dissemination of methodologies and tools for software engineering. This July, SEC changed its name to Software Reliability Enhancement Center and focusing on more improvement of reliability. So this is the agenda for my presentation. First, I will talk about the importance of software in IT systems. Then I will discuss how it is difficult to develop the software which is intangible. Additionally, as IT becomes more widespread throughout society and can be used by anyone, IT-related problems are increasing. To prevent these problems, it is important to improve the quality of software that play an important role in IT systems, and also to maintain resilience so that if a failure in hardware or software occurs, the safety of systems itself is guaranteed. In this sense, I also will introduce some of SEC's efforts to improve the quality of software. Since recently, software has launched only in computer systems. Today, a wide variety of devices surrounding us are equipped with software, and the operation of these devices are generally controlled by software. Among these devices are automobile, airplane, and train. That could be become a direct threat for our lives if they fail. Therefore, the role of software to maintain secure socioeconomic activities is getting significantly more important. This graph shows the changes in market size and number of employees in the software industry in Japan. So the figure cannot be simply compared with the preceding numbers because statistical statistics were revised in 2006. Both market size and the number of employees have trended upward in these years, creating a large scale of market industry with almost 20 trillion yen market size and almost 1 million employees. Comparing with other industries, for example, steel industry has 230,000 employees, and electronic parts and devices manufacturing industry has 530,000 employees, indicating how large the industry is. These graphs show the changes in the size of software embedded in various devices. The software size is expressed in the number of program lines. The size of embedded software in all devices has increased exponentially for the years shown. For automobile, the size has grown by a factor of 10 over these 10 years. And the number of program lines is over 10 million lines, and we expected to reach 100 million by 2020. 10 million lines easily exceed the size of online banking system in 1980. And at that time, the software of this size ran in a large-scale mainframe computer. But today, this size of software runs in a thin car. This chart shows the breakdown of the cost for embedded system development. Today, the software development cost is over the half of the total cost, at least 50%. Mr. Thomas said that it is 80 or 90%, but I'm not sure. Generally, it is considered that hardware development cost is greater than that for software, but actually it has been reduced to only 1/4 of the total cost. As I mentioned before, the importance and the size of software is increasing significantly in IT systems. However, being intangible, development of software involves some difficulties. Especially since system development is a logical simulation of social systems and business models in society, it becomes more complicated as society becomes more complicated, and so on. Professor Brooks of the University of North Carolina and leading expert of software engineering says in his famous book titled "Milestone Unlocks" that the difficulties of software development are as follows. That is, adding manpower to the late software project is this is known as Brooks' law. This is because it takes time for people added to project to become productive, and also the communication overhead increases as the number of project members increases. He also says in his article titled "No Silver Bullet" that there is no breakthrough development equivalent to the silver bullet bridge, which defeats the werewolves with a single attack, expected in the field of software development within the decade. Here, werewolves refer to delays of development schedule and expanded costs and low quality software. To understand the actual situation in the field of software development, SEC analyzed data on actual projects supplied by selected companies. This graph shows the relationship between workload and work period for new development projects. The vertical axis represents the work period in months, and the horizontal axis represents workload in man-hour. And the pink line shows the upper and lower limit obtained from regression analysis conducted at 50% reliability. As clearly shown in this graph, work period and workload are non-proportional. As work period increases, workload tends to increase exponentially. This suggests that Brooks' law is still valid. This graph shows the relationship between planned and actual value for development time of the software. Again, vertical axis represents the actual number of program lines, and horizontal axis represents the planned number of program lines. On the green line, actual value and planned value match that the orange line obtained from average projects is located above green line. This means that actual size exceeds grant size by about 10% on average. Similarly, this graph shows the relationship between planned and actual value for development workload. Again, the actual value for workload exceeds the planned value by 20% on average. Because MAC errors comprise of most of the development costs, we can conclude that development costs will increase from the planned value by 25% on average. Although the above is the result of analysis of data from suppliers, we can guess that the data from the users will indicate more severe results. According to a survey of Japan Users Association of Information Systems, that is an industry group of user companies, that more than 40% of the user companies responded that large-scale projects with 500 months or more were delayed in completion. In addition, about 36% of the user companies responded that medium-sized projects were delayed in completion. Just like the system development period, almost 35% of user companies responded that expenditure for system development exceeded the budget for large-scale projects. And also, 30% of the user companies responded that expenditure exceeded budget. We can see that as the size of software is increasing and it is becoming more complex, so it is expected that the system development project will be less likely to be completed according to the plan, unless we take appropriate action. If system development project does not go as planned, it will adversely affect the quality of the development system. This graph summarizes the number of system failures that had significant effect on socio-economic activities in Japan based on first releases. The number of incidents dropped in 2009 on average 1.3 per month. Since then, however, it has been growing for decades. In 2012, the number of incidents averaged 2.8 per month, which is almost the double of 2009, and is back to the level of 2007. These are the examples of recent IT system failures which have significant effect on society. Okay? For example, in February last year, we had a big disinflation in the stock exchange. So, question now is, what should we do to prevent these IT system failures? Basically, we must implement two initiatives. First, though it is nothing surprising, we must develop high-quality software that serves as the core of the IT system. Then we must maintain resilience in such a way, even if failure in hardware or software will not have actual effect on the user. In the following slide, I will introduce 5 SEC efforts to fulfill these initiatives that are high-quality development in upstream process, development of high reliability embedded systems, visualization of software quality, building high resilience systems, and improvement of reliability of critical infrastructure. First, I will talk about the high-quality development in the upstream process. Normally, software development follows the big model shown in this chart. This is also called as waterfall development. But the agile development, which has been drawing attention recently, allows for repeated prototyping. However, this development approach is not so widespread yet. The upstream process refers to the requirement definition process in the B model. In addition, the process above the upstream in which management strategy is determined is also called super upstream. These two processes may also collectively call the upstream in a broad sense. In the upstream process, the role and the purpose of software to be developed is defined. So it is the most important step in software development. The actual project data we collected indicates that workload differs with each process. The most intensive process is production process, that is programming process, which represents almost 1/3 of the total workload. However, the workload for requirement definition process is the smallest among the other processes, account for only 8%. Production process and test process can be automated in some extent. So the more human resources should be allocated in the upstream process. From the user's viewpoint, the top reason for delay in system development is delay in decision of requirement specification, followed by insufficient requirement analysis. Both are defects in the upstream process. Almost 37% of all defects are upstream. survey conducted in the US, the cost of removing a single bug decreases exponentially as we go into the lower green processes. The survey reported that related costs for requirement definition process is one. Test process costs 20 to 30 times more, and the operation process requires 150 greater cost than the requirement definition process. This suggests that detecting bugs earlier in the upstream to improve the quality of software has also cost advantage. So, to improve the quality of the upstream, requirement must be clearly defined in both functional and non-functional. Of this type, functional requirements are directly linked to services and businesses that user need to develop. So they are easy to define, and users can explain them in their own words. So both the users and developers will be less likely to omit these items, and requirements can be determined appropriately. On the other hand, non-functional requirements such as response time or expected throughput are more technical and specialized in nature. So users have some difficulties in understanding what they demand. And consequently, building a consensus with the developer will be likely to be delayed. And further, the resulting agreement will be likely to be ambiguous. So the important point here is it is quite important to define requirements, especially for non-functional requirements. We create and release template containing items that must be determined to avoid omission while non-functional requirements are defined. This table is an example template. By using this template, you can determine items related to availability, scalability, maintainability, or security without missing something, and can improve the quality of the upstream. Another effective measure to improve the quality of the upstream process is to use formal methods. Using formal methods in software development has various advantages, including elimination of ambiguity in specifications and verification of the correctness of specifications and design. Recently, many tools have emerged for practical use, and their applications to certain important infrastructure systems have been reached in many countries. This graph shows the result of our experiment performed to verify the effectiveness of applying formal methods to the design documents for systems already in use. investigation of the external document detected a total of 55 defects. Of these defects, 35 were determined to require or desire modification due to their impact on the systems already in use. In this way, defects that cannot be found through human review can be detected by using open methods. Next, I will talk about the development of high reliability embedded systems. This lab shows our investigation in causes of IT system failures occurred in countries outside Japan. The level of IT introduction per country is classified into 3 groups based on the Internet division data. The result says that in countries with low IT introduction level, the ratio of problems in enterprise systems is high. While in countries with high IT introduction level, the ratio of problems in embedded systems is high. So we can see that as the internet spread and IT become more related to our social life, embedded systems play an important role, and the development of high reliability embedded systems become more important. Because embedded systems are created by embedded software within various devices, development of embedded systems has unique difficulties apart from that of enterprise systems. Since devices are intended for diverse environments and purposes, they face the different constraints such as size or time. To support this unique development, we at SEC collected actual case from actual project, and simply summarize this case as best practices and release them to be widely used as reference. We summarize this reference as ESXR. ESXR stands for Embedded System Development Example Reference. ESXR covers all the processes in D model. In this case, blue guidebook is a reference for development management, and the orange one is a reference for development work. This guide, ESCR, summarizes the coding reference for software development using the C or C++ language. This book explains the description method that should be followed to improve the quality of coding, presenting a specific example. Today, ESCR is widely used in various countries and is referred to in ISRC as the international standard for development of embedded systems for automotive. Next, I will talk about the visualization of software quality. Some of you may be aware that from 2009 to 2010, the number of acceleration in Japanese e-goods in the US increased rapidly. The problem was suspected to be the software for the electronic throttle control system. But the automaker was unable to explain the safety of the software. In response, MHDXA requested NASA, a third-party institution, to investigate whether the Japanese e-goods had defects. NASA tested the software but failed to identify the fault. Because the supplier of products has responsibility as the manufacturers, and that such kind of incident will have direct impact on their business. They struggle to supply high-quality products. However, even if suppliers proclaim their safety and high quality, the users will not be convinced by the related by their own assumptions. At least this example, the quality must be verified by a third party, and the result must be explained to the users in an easy to understand way. Since software is intangible, it is extremely difficult to explain software quality to the users in an easy to understand way. To explain software quality, it is necessary to present conditions such as intended users, services, utilization situations, and constraints, and the expected quality goals based on these conditions, and development process required to achieve these goals together with evidence. However, this effort cannot be understood by the general user. In addition, explaining software quality is getting difficult for product suppliers. As the size of software increases and it is run in collaboration with a wide variety of external systems in the network, so it is getting more harder for product suppliers to understand the quality status for their overall system. And also, external software added using open source or cloud services. The quality of these software is not guaranteed by a client supplier. Under these circumstances, it is necessary to introduce a scheme where independent third party verifies the quality of software, and verification results must be explained to the users in an easy to understand way. To ensure fairness, we create a guide listing minimum items that should be observed in the implementation of a scheme for third-party quality verification. And we are promoting the spread of this guideline. The first application of this guideline authority certification for update software that we launched this June. Next, I will talk about the construction of high resilience systems in the face of failure. After experiencing the Great Japan natural disaster not share. So to respond to these needs, we collected actual case following the disaster and summarized and issued the guide for introducing high resilience systems, in which these cases were analyzed and systematized by experts. According to our survey, companies are becoming aware of the need for BCP. In large-scale companies, especially, the percentage of those with BCP is increased by about 10%. But in the SME companies, they also aware of the need for BCP, but not yet developed. The survey also discovered that within the companies who have BCP and define the RTO to less than 6 hours, 1/4 of those companies do not have system redundancy. So to support in solving these problems, we produced the guide for introducing high resilience systems as a guideline when considering BCP. The systems are classified into 3 major models, and the main requirements that should be satisfied are defined for each model, by each model. Finally, I will talk about the improvement of reliability of critical infrastructure. The provider of critical infrastructure that are essential for our social life, such as electricity, gas, railways, and financial services, have striven to improve the reliability of those infrastructures by taking most advanced and ex-post measures in preparation for predicted failure. However, the important know-how and experience are not shared among the company or different industries. There is a tendency to keep the failure information within the company. Lessons learned, learning from our failures is a meaningful method and the system of sharing information as lessons learned is required in terms of recurrence prevention. On this background, SEC has launched an initiative in which we collect failure cases from cooperating companies, and experts analyze these cases, and we summarize and release the information as lessons shared, as lessons learned. We do not believe that these lessons must be uniformly applied to all companies or industries. Our approach is that lessons are classified into grades depending on the risk level or effects in event of failure. In summary, today the IT system and services supporting our social lives cannot exist without software. They are also growing rapidly in importance. On the other hand, because it is software development difficulties not presented in hardware development. In order to prevent problems in IT systems, in addition to the development of high-quality software, we should consider the resilient system while assuming that the failure will occur in both hardware and software. Thank you for listening.
Thank you very much. Is there any question? My time is short, so one, two.
Thank you very much for this presentation. It's not a question, it's just a comment. I believe that this is really a very important topic, becoming more and more important, and especially for, let's say, technical systems like machines, cars, and others. It's, as you have shown in the beginning, more and more software inside, so it's really important. You also mentioned in your presentation some international standards, for example, the IEC 61508, which is on the so-called functional safety, covering the, let's say, the functionality, the availability of software, but also aspects of systematic failures of hardware, of the reliability of hardware. And just for information, tomorrow afternoon, I think in this room there are some presentations on functional safety. I will also explain a little bit how is it done in the different fields like machinery, battery management systems, and so on. And I really believe that this is a very important topic, and so thank you very much for this presentation here. Thank you.
Thank you very much.
That was a very comprehensive coverage, and there are many points I'd like to ask. But one I'd like to ask right now is the use of formal methods. The trouble is, most of the problems in systems occur at the interface, but formal methods are not very good at defining interfaces. They are good for functions, but not the interfaces. Do you agree?
I'm sorry, I'm not an expert on formal methods. So maybe it is true something. In case of our experiment of experience, in case we use the formal method for external design document. This document defines the interface between the systems. So in some sense that formal method for very useful for defining international interface between the systems.
There must be many other questions, but let me stop here. Please join me in thanking Dr. Matsumoto.